Okay, so let me share my screen. So can anyone confirm that if you can see the screen?
Yes, sir, it is visible.
Okay, thank you. So good afternoon. Today, as you know, we were looking at uh, substitution permutation network SPN, and I'm going to show you the attack on SPN. And before that, I'll complete the background. And as you know, whatever I am covering is part of private key crypto system or symmetric cryptography. And so what was a block cipher? Actually, we were looking at block cipher. So it is a iterated cipher. There are round functions and key schedule. And there is a public algorithm to generate the key schedule, right? And encryption of a plain text will proceed through n similar rounds, right, using a key schedule. So we have, normally uh, we have the state. A round function is a function of state, previous state, and the RS. So it basically the current key, So that is how you compute. So this WR is equal to G of WR minus 1 KR. Okay, WR is a state. And the initial state W0 is the plain text. So basically we had something like this. From plain text, we compute the next state using corresponding keys. Finally, we get the uh, ciphertext Y after n rounds, right? And I think because the function should be injective so that we can do the inverse. And then we have, G inverse of this condition should be satisfied, right? So given a ciphertext, it goes to round n, and then you go to one less, and so on. Finally, you get the plain text. So everything is inversed, So this is the way we can get plain text from the ciphertext. Now the substitution permutation network consisting of two components, substitution boxes or S boxes called pi s, and permutation. So pi s is permutation of bits, of length L, and this is permutation of numbers, in some orders. Okay, so plain text is a binary vector of length Lm, and ciphertext is a binary vector of length Lm. Okay, Lm is known as block length of the cipher. Okay, so this is pi s and pi p. Okay, so given an Lm bit binary string, we can define x of its concatenation of m binary strings of length L. Okay, which are something like this. X, this notation, xi subscript this notation is nothing but xi minus 1 times L plus 1 and so on up to xil. Okay, so this is I'm just recalling what is SPN. So basically a crypto system SPN, substitution permutation network, consisting of, as you can see, a substitution permutation, and pi p a permutation, and then P and C plain text are binary vectors of length Lm, and there is a key schedule, right? So let me give you key schedule. So key is k1, k2, kn plus 1. Okay, so here it is. Here is the algorithm, how it works. Okay, so UR is the input to S box, VR is the output to X box, and WR is obtained from VR by applying pi p. Okay, and then UR plus 1 is coming from WR. Okay, so this is the basic algorithm that you are doing. So here is an example. So in fact, I am going to show you the attack also for this example only. So we have LMN is equal to 4, you know, and input space to output space, the pi s written in hexadecimal notations. This is your pi s and this is your pi p. You can see that. So all these hexadecimal numbers 0, 1, 2 up to F. Okay, and these are corresponding to binary ones. We can convert them into binary if you need. Okay, and then we have the permutation function. You know, it's changing the order actually. All the 16 elements. So here is a SPN. These are the boxes. You can see that. So this is U1. You know, one so then U2 1 and so on. This is for round 1. All the U bits are coming. These are the substitution things. S boxes. These are called as S boxes. And then there is a permutation. You can see that these bits are changing from here to there, here to there. You know, so for example, this bit is going here and coming this one, right, and so on. Okay. So and then there is a key. You can actually see that key is used in between. Okay, so this is the complete picture of a substitution permutation network, how it works with all these things: U1, V1, W1, U2, and so on. So states, input, output, these are the things. Okay, and how we construct the key through some algorithm. Here is a K1, K2, K3, K4, K5 from K, coming from K. You know, this is complete K, and from this the first 4 blocks are in K1, next 4 blocks in K2, and so on. Okay, now so this is a complete encryption using starting from X, we arrive at Y. Okay, all these states, all these bits are written here, you know. So this is a substitution permutation network. I'm just recalling. Now, in order to do the attack, we first we are describing linear cryptanalysis. So I'll focus on this example itself, where LMN is equal to 4 and this picture. So this picture, this example, we are going to look at actually for cryptanalysis. Okay. So what we do, so what is the strategy for linear cryptanalysis? Suppose it is possible to find a probabilistic linear relationship between a subset of plain text bits and a subset of state bits. That means there exists a subset bits whose exclusive OR behaves in a random fashion. It takes on the value 0, say, with probability bounded away from half. Okay, so that is a condition. So attacker suppose has a large number of plain text and ciphertext probabilities. You know, actually in this example you will see that they have something around 8,000 pairs. You know, which are needed. Okay, and so this is known as known plain text attacks. So what you do, for each of the pair, we will begin to decrypt the ciphertext using all possible candidate keys for the last round of the cipher. And for each candidate key, we compute the values of the relevant state bits involved in the linear relationship. Okay, and determine if the relationship holds. Okay, so I'm going to find out this relationship for this example. Okay, this is a general strategy. Whenever it does an increment to the counter corresponding to the partial decryption of a candidate key, you know, so corresponding to the particular candidate key, at the end of the process, we hope that the candidate key that the frequency count further from away times the number of plain text left, you know, contains the correct values for the key bits. So I think let me give you specific example now. So now before doing the calculations for this example, let us do what is known as piling lemma. So what I'm going to do now, I will look at each you know, like plain text, ciphertext, and in between, you know, the in bits like UI, VI, and so on, input bits, output bits, will correspond to the random variables, you know. So suppose x1, x2, dot 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 are independent random variables taking the values from 0 and 1, and suppose pi are the real numbers, you know, between 0 and 1. suppose that probability that xi is equal to 0 is pi and xi is equal to 1 is 1 minus pi, and I is not equal to j. So independence of xi and xj are independent variables. Now, basically, what is the probability that xi is equal to 0 and xj is equal to 0? This will be obviously if this is probability pi and this is probability pj, right? So the condition probability will be pi into pj, right? Similarly, for xi is 0, xj is 1. This is basically pi times 1 minus pj. Xi is equal to 1, xj is equal to 0. It is 1 minus pi into pj, and so on. We can compute all the probabilities. That means we can compute the probability of this sum xi plus xj. So xi and xj are random variables, right? Now this is 0. The probability will be 0. So this is 0. This quantity is 0 if both of them are 0 or both of them are 1, because 1 plus 1 is 0 and 0 plus 0 is 1, right? So for one of them, when both are 0, the probability is pi into pj, and when both of them are 1, the probability is 1 minus pi into 1 minus pj. So actual probability is sum of these two. Similarly, the probability of xi plus xj is equal to 1 turns out to be this quantity. Okay, so this is something interesting. Now I can define what is known as bias, the bias of a random variable. These concepts are going to be useful when we do the attack. Right now I am doing it for a general random variables. Later on, these random variables are nothing but these intermediate bits that we are using, and we're looking at the expressions. The bias of a random variable xi is defined as epsilon I is equal to pi minus half. Okay, so pi minus half. So observe that immediately that minus half less than or equal to epsilon I is less than or equal to half, right? Bias lies between this, right? Because pi is, we know where it lies, right? So that means we can define that the probability that xi is equal to 0 is nothing but half plus epsilon I, and probability that xi is equal to 1 is nothing but half minus epsilon I. Okay, obviously I is equal to 1, 2, 3 and so on. Now we can define what is known as Pileup lemma. So this lemma is useful in computing the biasness, of when there are, we are having a lot of linear combination of a lot of random variables. Okay, Pileup lemma. Okay, so suppose epsilon I1, I2, Ik, the bias of the random variable xi bar and so on, sum of these xik. So this is the bias of the random variable, sum of all these random variables, xi2. Then this value is nothing but then actually epsilon I1, I2, this biasness is nothing but 2 raised to power k minus 1 partial product j is equal to 1 to k epsilon ij. Okay, so now this is the Pileup lemma. Why we are doing it? As I mentioned, while doing the computation in the strategy, I told you we need to look at some of these variables, in the intermediate variables, right? So this is something will come quite often, and we need to somehow find the biasness of this expression. Okay, so the proof of this fact, Pileup lemma, is pretty simple by induction on k. So we can do it here. Induction on k. Obviously, it is true for k is equal to 1. Okay, and for k is equal to 2, what happens? K is equal to 2, we can see that probability of xi1 exclusive for xi2 is equal to 0. Okay, I'm just computing it for 0 actually, will be nothing but half plus epsilon I. Okay, half plus epsilon I1 actually. Yeah, I2 plus half minus epsilon I1 times half minus epsilon I2. And when you simplify this, this turns out to be half plus 2 times epsilon I1, epsilon I2. Right? Now you know that epsilon I1, I2 from this right hand side is what actually? Half. So essentially epsilon, it will be. So actually we are applying this formula, half plus 2 epsilon I1 epsilon I2 minus half. Okay, so this is nothing but 2 times epsilon I1 epsilon I2, which is the required thing on the right hand side. So this result holds. Similarly you can do for the other side, for 1 actually. So for k is equal to 2, result holds. Assume that it holds for k is equal to L. L is at least 2. And we want to prove that TPT that true for k is equal to L plus 1. That's what we want to prove. Okay. So now we consider xi1 sum of xil plus 1. We are taking L plus 1 variables. So this can be written as xi1 dot sum up to xil plus xil plus 1. Now we know that here the induction hypothesis will hold. Okay, so the biasness of this quantity will be 2 raised to power L minus 1 partial product j is equal to 1 to L times epsilon ij, right, for this quantity. And bias of this quantity is epsilon I L plus 1, right? So bias of the whole sum, we can actually compute what will be the biasness of the two sum, using the result for k is equal to 2, our previous result, this whole biasness of the whole thing of all L plus 1 variables actually, this will be 2 times 2 raised to power L minus 1 partial product j is equal to 1 to L epsilon ij into epsilon IL plus 1. This simplification will give us 2 raised to power L partial product j is equal to 1 to L plus 1 epsilon ij. Okay, so the result holds. So what we have done, we have used the result for k is equal to 2. Okay, because for k is equal to 2, result holds. I've used this result for k is equal to 2. So one portion is one variable we have treated, and the other portion another variable. This I have applied the induction hypothesis that result is true for k is equal to L. So this is this quantity, and then for this one, right? So sum will be product of this. Okay, so this is how the result holds for this. So that means now we will be using this result to compute the bias of random variable which is involving exclusive or sum of k variables. Okay, so this is something really important. We have a corollary also here. I should just mention here. 1 minute. We require more space. Okay, so anyway, so one corollary is there to this bias. So suppose epsilon ij is equal to 0 for some j, then epsilon i1 ik will be 0 actually, right? Because one of them is 0. Okay, so this lemma holds in general only when random variables are independent. Okay, this holds when random variables are independent. Now actually we can compute anyway, so this is something a small result actually. Now we are ready to show you the linear approximation for S boxes. Okay, how this attack will work, I am going to show you now. What we are going to do, we are going to do the linear approximation of S boxes. So you see in the picture here, we have this. Some of the variables will be involved here, you know. Okay, so basically some of these variables will be involved here, and then we try to guess the key bits. Okay, that is a trick actually. So let me show you in details how this works. So I can give you a general strategy now. So pi s is a S box from M to 0, 1, n. Okay, this is a S box. We do not assume that pi s is a permutation or even that m is equal to n. You know, this works in general anyway. Now choose an m tuple x is equal to x1, x2, xm, uniformly random from the set 0, 1, m. Okay, random. Okay, each coordinate xi defines a random variable. Now each coordinate defines a random variable xi bar. Okay, so if I pick up an xi here, I'll have a xi bar here. Okay, taking on the values 0 and 0 or 1. Okay, taking on values 0 or 1. Okay, and having bias epsilon I is equal to 0 for that particular random variable. Now these m random variables are independent. So if we have an output as mn tuple, y is equal to y1, y2, yn, this is your output. Okay, each coordinate of yj also defines a random variable. Each coordinate of yj defines a random variable yj, taking on the values 0 or 1. Okay, so these random variables are not independent from each other from the xis. Okay, in fact we have the following formulas. I would like to mention that. The first one, that probability of x1 bar is equal to x1, xm bar is equal to xm, y1 bar is equal to y1, yn bar is equal to yn is equal to 2 raised power minus m. Sorry, this probability is 0. This probability is 0 if y1, yn, this is the output, does not equal to pi s times x1, xm. Okay, this is the first property. Second property, that probability of x1 bar is equal to x1, xm bar is equal to xm Okay, y1 bar is equal to y1 and yn bar is equal to yn is equal to 2 raised power minus m if y1, y2, yn is actually pi s of x1, x2, xm. Okay, so these are the two important results depending upon whether input vector, output vector is a function of the input vector or not, right? So we have these probabilities, you know. Now one can compute the biasness of a random variable. So I think I would need more space here. So one can compute the bias of random variable xi1 xi p yj1 yjl. If this kind of expression is involved, I can compute the bias of this random variable. A linear cryptographic attack can be mounted when a random variable of the above form has a bias that is bounded away from zero. So attack can be mounted. So we will compute this actually for our specific example. When above form has bias that is bounded away from zero. Okay, then we can attack can be mounted actually. So now in our previous example, we know that bias is actually 0, 1, 4 to 0, 1, 4, right? Everything is 4. Ln m is equal to 4, right? So random variables will be x1, x2 up to x4, x4, y1, y2, y4, right? These are the random variables, all 8 variables, right? So possible values taken on by the 8 random variables. I think now we can see that here are all 8 variables, random variables defined by the S boxes, x1, x2, x3, x4, y1, y2, y3, y4, all possibilities I have written here. Now I can show you as an example, we will look at one specific case, say x1 plus x4 plus y2 and compute the biasness, okay? Because I'll be doing this in general here. So I'm looking at x1 bar, x4 bar, y2 bar, okay? So the probability of x1 bar plus x4 bar plus y2 bar is equal to, first you need to count number of rows in the table, and we know this value is 16, right? Sorry, 8. There are 8 rows in the table, right? Divided by 16. So we are actually counting number of rows in the table for which x1. So actually this is 0. Yeah, I'm counting it for 0. So when this probability is 0, so x1 bar plus x4 bar plus y2 bar is equal to 0. So in this table we are looking at when these values are, when this sum is 0 actually, okay? X1 bar plus x4 bar, x1 bar plus x4 bar plus y2 bar. When this sum is 0, we are looking at in the table, okay? For example, this is the one, right? When the sum is 0. So we can compute how many times this happens, and that turns out to be 8 divided by 16. So this is half. Okay, so this probability is half. Therefore, bias of this random variable is equal to 0. Half minus half, which is 0. Okay. Similarly, you can compute that bias of x3 bar, x4 bar, y1 bar, y4 bar is equal to minus 3 by 8. This you can verify. I'm just giving it to you. This expression is minus 3 by 8. In fact, one can compute the bias of all 2 raised power 8 is equal to 256 possible random variables. Okay, so we can write in general, each random variable can be written as summation ai xi bar, okay, I is equal to 1 to 4 plus summation I is equal to 1 to 4 bi yi bar. Okay, so where ai and bi's are numbers belongs to 0 1, I is equal to 1 2 3 4. Okay, so if in general each random variable can be written as this, so we can actually use a compact notation. I can write it down as A1, A2, A3, A4 because these are the things which vary. B1, B2, B3, B4, right? These are the binary things, and we convert them into hexadecimal notation. Okay, so this we call it as input sum, and this will call it as output sum. Okay. So each 256 random variable has a unique name as a pair of hexadecimal digits, So we can write it down as a hexadecimal digit, For example, let me show you x1 bar, x4 bar, y2 bar. So this can be written as 1001, right? 2 3 is missing here, and this can be written as 0100, right? Only 2 is present, y2 is present. So that means this goes to 9 in hexadecimal notation, this goes to 4. So the whole thing can be written as 9 comma 4. This variable can be written as 9 comma 4, right? So all these combinations we can write down a combination like this, right? So that means uh, for a random variable we can define, for a random variable having hexadecimal input a. So if the input sum is a is equal to a1, a2, a3, a4, this is the hexadecimal, and output sum b is equal to b1, b2, b3, b4. Okay, and we can define NLA comma b as number of binary 8 tuples so it's like x1, x2, x3, x4, y1, y2, y3, y4, okay, such that y1, y2, y3, y4 is equal to pi s times x1, x2, x3, x4. Okay, and of course we have that summation AIXI. Sorry, we have sum like this: I is equal to 1 to 4 AIXI, sum of I is equal to 1 to 4 BIYI is equal to 0. So we can actually say that the bias of the random variable, we are going to use these formulas later on. Bias of the random variable having input sum A and output sum B. B is epsilon A comma B is equal to NLAB minus 8 divided by 16. This is a general formula. And actually, for our example, NL94. So I think in our previous example, I can see that NL94 is 8. Okay. And so this implies that epsilon 9 comma 4 is equal to 0. Bias is 0. We can compute from this formula as well. Okay. So the table of all values of NL is called the linear approximation table. Okay. So this is our linear approximation table. Here is the table, or NLAB is mentioned here for A and B. Okay. Okay, so this was all machinery that that was required. Now we can look at the very specific example and see how I'll give you a very specific algorithm how actually this is going to work. Okay, so as you can see here, so I'm because it's a bit lengthy procedure, so I'm again revising few things. So what we are doing, what we have covered till now in the piling lemma business, we want to compute the biasness of random variables, which are something sum like this, right? Or in general, a sum like this. Okay. How do we compute the biasness? This is what we need to compute. Okay, because that is going to be useful for us. And in our general strategy, we see that this biasness is going to help us. Okay, now I'm going to show you one very specific example. So in our the previous example that we were looking at, okay, so this example, again I'm going to now I'll show you a linear attack on this SPN. So how do we do this? So we need so linear cryptanalysis requires finding a set of linear approximation of S boxes that can be used to derive a linear approximation of the entire SPN, for this entire SPN, except last round. So we can look at this picture here. I think I might be having a picture of the linear approximation here. Yes, here it is. You see. So what are the active S boxes that are involved? S21, S22, S23, S43. Okay, and these arrows are there. So lines with arrow correspond to random variables that will be involved in linear approximation. So these are the arrows. So for example, this one, okay, is going to involve. This is known as these are the random variables basically which are involved. Okay. So how do we compute this? Let me show you. You can see that this is U51. Okay, round 1, U51. This variable is U51. U51. Okay, this is this 1, 2, 3, 4, 5, 6, 7, 8, right? So 8, 9, 10, 11, 12, 13, 14, 15, 16. All these 16 things are there. Okay, so we denote it by UIR is a random variable corresponding to the inputs of the X box. Okay, so 1 less than equal to I less than equal to R. So these are the info. For example, this U51 will be the random variable. Okay, similarly, we have VIR is the random variable corresponding to the output of the S box. Okay. So actually, I can look at S21. What is happening here? S21. S21 we can see here basically T1. I mean, I'll call it as a T1 variable. Okay. T1 is equal to U51. U51 is this. Okay. Plus 6. 6 is not there. 7 is there. 8 is there. U71 plus U81 in round 1. Okay. Plus, so these are the input variables, right, to this S21 box. And there is one output. Which output number is this? So 1, 2, 3, 4, 5, 6. 6 is there. So this is plus V61 in round 1. Okay, this is a variable T1. I'm just calling this T1, this sum actually. Okay, so you can see that by our previous results that this T1 has bias, 1/4. Similarly, we can compute T2. T2 is, I am calling another variable. Now I look at second one, S22 here. So this is actually 1, 2, 3, 4, 5, 6. 6 one is a input variable which is going here. So this is U6 to second round, right? This is going as the input variable, and output is one here and one here. This arrow you can see here. Okay, and one arrow is here. This is U62 plus V62 plus V82. Okay, this is second variable. I am calling it T2. This also has bias. Actually, you can compute minus 1/4. Okay, then we go to T3 here and T4 here. I mean, for this one and this one, actually, for both the active bosses, I'm just writing what happens to T3 will be V63 plus V6. Sorry, U63 plus V60. This is U63 plus V63 plus V83. And this has also bias minus 1/4. Then we have T4 is equal to U14P plus V14P plus V16 3, and this has also bias minus 1/4. So here the bias is 1/4, here the bias is minus 1/4, here the bias is minus 1/4, here the bias is minus 1/4. Okay, minus 1/4. Okay, so the four random variables have bias text are high in absolute value. These are having high in absolute value, right? So if we assume that these four random variables are independent, which is actually not the case. I mean, this is something very interesting actually. Now we assume that these random variables are independent, which is not the case actually. Okay. Now we can use we can apply Pileup Lemma, but actually it works. Still it works. So we assume that they are independent. Even though they are not, and you see we do the calculation and see that it works. Using Pileup Lemma, we can compute the biasness of T1, T2, T3, T4 for all these sum. Now actually I will use these key bits here because you see keys are involved here, right? K1, K2, K3, K4, K5. So I can simplify these things. I can expand this T1, T2, and then I can simplify this sum. Okay. Actually using Pileup Lemma, we can compute the biasness of this is 2 cube times 1/4 into minus 1/4 cube, right? By Pileup Lemma is equal to minus 1/32. right? Because we know that this has T1 has bias as 1 by 4, T2 has bias minus 1 by 4, T3 has bias minus 1 by 4, T4 has bias minus 1 by 4. So then applying piling up lemma, the bias of T1, T2, T3, 4 turns out to be minus 1 by 32. Okay. So now I am going to, now you see there are other interesting relationships. For example, U62 is V61 plus K62. Okay. U6, this is U. Input in the 6th round. Okay. Okay. In this, basically K26. 1, 2, 3, 4, 5, 6. This is there. You see. Okay. So these kind of expressions are there, which we can look at the figure and find it out what are the relationships. So input here. Okay. Okay. In which round we are looking at? Second round is output of the first round for the 6th bit and summing it with the 6th bit of the key, the second round. Okay, this kind of relationship we can look at from the picture itself. In fact, from this we can say that I will need more space here now. Okay, so using these kind of expressions, we can compute T1 bar, the first random variable T1 bar as U51 plus U71 plus U81 plus V61. Okay, which can be further expanded as x5 bar plus k51 plus x7 plus k71 plus x8 plus k81 plus v61. Okay, so we are just using the above kind of relationship. We can find T1 is this. Similarly, T2 turns out to be U6 plus V6 plus V8. This is 2, V6 is 2, and U6 is 2 is equal to V61 plus V61 plus K62 plus V62 plus V82. Okay. Similarly, T3 will be U63 plus V63 plus V83. Turns out to be V62 plus K63 plus V63 plus V83. Right? And T4 is nothing but U143 plus V143 plus V163 is equal to V82 plus K143 plus V143 plus V163. You know, so all we are using these key bits and expanding these variables. Now, as you know, we are going to compute the sum. So sum of these T1, T2, T3. So some of them will cancel with each other, right? For example, this V61 and this V61. When you sum, these two will go off. Twice of this will be 0, right? So like this, when we add all of them, we actually get summation over Ti is a random variable from I is equal to 1 to 4. This is x5 bar plus x7 bar plus x8 bar plus V63 plus V83 plus V143 plus V163 plus K5 1 plus K7 1 plus K8 1 plus K6 2 plus K6 3. These are all random variables with respect to key, right? K14 3. So this has bias -1/32 as we saw earlier, right? Now I can further do further reduction by using the following key, that V63 is nothing but U64 plus K64. Similarly, V83 is equal to U144 plus K144. Okay, then V143 is equal to U84 plus K84, and U16, sorry, V16 P is equal to U16 4 plus K16 4. So again, we are using these kind of expressions inside this summation, and finally we arrive at something called I is equal to 1 to 4 x5 plus x7 plus x8 plus u64 plus u84 plus u144 plus u164 plus k5 plus k71 plus k81 plus k62 plus k63 plus k143 plus k64 plus k84 plus k144 plus k16 4. So basically we have these expressions of plain text bits, then corresponding to these inputs UIs, and then we have this large, you can see that this large one for key bits. Okay, so plain text bits plus bits of U4 and key bits. This is a combination of summation of all these things, right? So if we assume that the random variable, this expression from here to this and this whole portion here. So this random variable, suppose, has a fixed value 0 or 1. Okay, then this summation will simplify to x5 bar plus x7 bar plus x8 bar plus u6 4 plus u8 4 plus u14 4 plus u16 4. This we call it expression 4.3. This is an important thing. This has bias equal to ±1/32. Sign depends on the value of the unknown key bits. Unknown key bits. Okay, so this is the expression that we are going to use actually to do the attack. So I think we are going to do the attack in our next class. So using this expression, we are going to use this expression, and I'll tell you the basic algorithm through which we can bound the attack. Okay, So I think that's all for today. If you have any question, please do ask me. So okay, so this is the basic strategy that we are telling you, and that is also through an example. Okay, I'm showing you everything by an example, and so finally I will tell you the attack, how the candidate subkeys are one can find the candidate subkeys. Okay, and there is a specific algorithm which we are going to show you in our next class. So thank you very much. See you in my next class. And after this attack, we are also going to show you another attack known as differential cryptanalysis. Okay. So then after that, we are going to talk about DES, Digital Encryption Standard, and AES, because SPN is a special kind of iterated cipher, kind of simple iterated cipher. With some modifications, we can get DES and AES. I'll show you how those things are different. Some of these ideas are used there in digital encryption standard and advanced encryption standard, which are two popular crypto systems which are used widely. Okay, so we are going to discuss those things in our next class. Thank you very much.